So far, we have seen how convolutional neural networks learn powerful spatial features using convolutions, pooling, and deeper hierarchies. See, there is a trade-off though. As models get deeper and more powerful, they also get larger, even with CNNs, slower, and more expensive to train. That raises an important question. Can we get most of the representational power of convolutions, but with far fewer parameters? That's exactly what depthwise separable convolution layers are designed to do. In this video, we'll break down how they work step by step, how they differ from regular convolutions, and why they're widely used whenever efficiency matters, like MobileNet. So to understand depthwise separable convolutional layer, let's first look at the regular conv 2D layer, which we have already seen in the previous video. I'm putting it here so that you can compare how the depthwise separable convolutional layer is different from the regular conv 2D. So regular conv 2D, again, you take a color image, right? 3 channels, 32 by 32 pixels, right? Then you take a filter, single filter. The filter's depth would always be the same as the input's depth. This doesn't have to be the input pixel. It could be any input to a regular conv 2D layer, right? Whatever the filter depth is, by default, see this 3, 3, that matches. So you take if it's a 3D, right? In the input channel is 3-dimensional, or your filter depth will be 3D. So you take that, put it here, right? And when you do the convolution operation, you'll get a single value, scalar value. And as you convolute through the entire input data, right? For each filter, you'll get one surface in the output, one 2D surface. So if you have 10 filters, you're going to get 10 surfaces. So basically the output would be 30 by 30, 10. So this is your regular convolutional 2D, which we have already discussed in the previous videos. You can please go back to that, introduction to CNNs, where I have talked about the convolutional 2D layers. Now let's talk about the depthwise separable convolutional layer. It does something similar, but it does this in stages, in 2 steps. Okay, so what it does, again, you take an input image, a color image, 3D color image. You still have 3 channels, 32 by 32 pixels, and 3 channels, red, green, blue. Okay, so now let's look at the filter. Now the filter, again, depthwise separable convolution process happens in 2 steps. In the first step, the filter is still 3 by 3, but see, the depth is now 1. Basically, it's a 2-dimensional filter. So you take this 2-dimensional filter, put it on the, let's say here, the red surface, the red channel. You convolute this, you get one surface. Okay. Now take the filter again, put it on the green, convolute it, you'll get another surface. And similarly on the blue, you'll get another surface. So use a single 2D filter, convolute the 3 channels, you'll get 3 surfaces. Okay. And the shape would be 30 by 30 by 3. Okay. So this would be the first step. This would be the depthwise convolution. Okay. Now what we're going to do is we're going to do a pointwise convolution on this 30 by 30 by 3. What is a pointwise convolution? So now you take, right, a 1 by 1 filter, because the filter size is 1 by 1. But the depth of the filter would again now match this 3, because the input would be the 3. So it would match whatever the input is given to this point convolution. So the depth would be 3. So you take this guy, right, and you put it on that. You do the convolution, right, and you'll get one surface. So now if you have 10 filters, right, you'll get 10 of these surfaces, and your output shape will be 30 by 30 by 10. So the first step, this would be the depthwise convolution. And the second step, this would be the pointwise convolution. So basically, in essence, you're still getting this output of 30 by 30 by 10, something similar. But you see, the magic is that with depthwise separable convolution, the number of parameters will be far, far less. You will see this, like, when we're going to do a project, we're going to use this depthwise separable convolution layer. And as you can clearly notice that it dramatically reduces the total number of weights that needs to be trained. And the performance will be as good or even better. So that's the magic of depthwise separable convolutional 2D layers. So again, what are the advantages here? Significantly fewer parameters to train. Models can converge much faster because fewer parameters, and it also is less prone to overfitting. So that's the intuition behind depthwise separable convolution layers. See, they don't change what convolutional neural networks learn, but they change how efficiently they learn it by dramatically reducing the total number of parameters. See, this idea plays a big role in modern lightweight architectures especially designed for speed and scalability, like say in edge devices. In the next few videos, we'll continue building on this foundation by looking at what happens as the networks get even deeper and the challenges that arise during training such deep neural networks. If you're following along, please make sure to check the full Deep Learning Foundations playlist linked below. Happy learning.